I'm from NASA headquarters. I'm the director of the Advanced Communications and Navigation Division within the Space Common Nav program. And I'm tasked basically with finding and developing with my division the advanced comm systems that NASA would like to fly. If I could type my password in here, I'd be set. Okay, we're in. Great. Would like to fly, well, some of the systems that we've developed and flown in the past, in the last 2 years, and then some things that we have at work in the future, and they're all excellent opportunities for DTN. We've done actually several DTN experiments on some of the past missions that I'm going to talk about today, and Dave Israel will talk some more about that. But this is also more about the future, and that's what we're hoping to illustrate here. Next slide, please. So one system that we actually launched in 2012, and it's currently on the space station right now, is the SCAN test bed. And that is a system that is all radio frequency based. It's currently a platform on the outside of the space station. It's a hosted an extended facility payload that was brought up in 2012. And it's a facility that includes an S-band radio, a Ka-band radio, a GPS receiver, and the ability to do DTN experiments. And the reason is because this system is actually based on software-defined radio technologies, and it also has software-defined computational ability and storage as well. So the devices are all reconfigurable, and this is something that we'd like to work into our missions in the future, and so this is an opportunity for us to do experiments on how they function. This system, of course, is ready for space use, and it's reconfigurable. We've been doing experiments since 2012. This is an opportunity to do this not as what we saw before with the ISS team, who's actually working with the operational folks, but to do pure experiments. We actually do not have a data connection to the space station here, so in some ways I guess that's a plus, because there's no way we can come back and corrupt anything that's being done operationally. But that also gives us free rein here then to do experiments as we like. And so, as I said, many major things have been demonstrated here, including the software-defined radio, which is Ka-band. We've actually been able to upgrade both the error-correcting coding and the modulation there, so that I think now at this point we're at a 16 QAM system that can do 575 megabits per second through TDRS into the ground. So again, that's a great experimental capability. But what I want to talk about really today are the opportunities of what's being done with DTN. Next slide, please. So the objective here is to implement DTN with CFDP and an on-orbit platform, and of course do experiments to advance the state of DTN. We are also very focused on implementing secure DTN protocols with current state-of-the-art cryptographic standards. I'll talk a little bit about that. What's planned right now in FY15 is we're actually doing an international program where we're going to do a DTN experiment with CNES, which is the French space agency. It gives us an opportunity to validate what we're doing in CCSDS, because that standard is, of course, an international standard being developed in the standards bodies, and part of doing a standard is you need to go off and actually do experiments and see if two separate agencies can get the same answer and work together. And so that's one of the opportunities that we have there. That's being done this year. Next year, we're actually looking at multi-hop DTN experiments in FY16 that will also use adaptive networking. So one of the things that we're hoping to demonstrate on the SCAN testbed in the future is adaptive coding, adaptive modulation, being able to adapt the system and have it what we call cognitive networks. And so we hope to build a bit of intelligence in by monitoring some of the parameters of the system and adjusting. So for example, as the link degrades, maybe because the distance gets larger, you may in fact reduce the bandwidth of a system by turning up the error correcting code. and turning down the bandwidth. And you can increase the overhead of the error correcting code, for example. So that's something where you'd monitor the link parameters, such as the error rate before the correction, and adjust the system accordingly. That a lot of back and forth is required for that. I think in the future we need to make sure that those systems will be well compatible with DTN. Another thing that we have going is there's an SBIR with a company called InnoFlight that's doing some work for secure DTN. That's going to be demonstrated in the FY16 timeframe as well. Next slide, please. So I'm also going to talk about our efforts now really for developing higher bandwidth communications links, which you'll find actually are very applicable to, are really a killer app, so to speak, for DTN. So NASA needs more bandwidth in its networks in space. So here's a picture of one of our rovers on the surface of Mars taken at 30 centimeter resolution. Next, please. On the edge of Victoria Crater. Next. And of course, Victoria Crater off to the side here on Mars. Next, please. And so if we wish to transmit a 30 centimeter resolution Google map of the entire surface of Mars at just 1 bit per pixel, by the way, that's about 10 to the 15 data points. Next. And so the best RF system that's been flown to Mars to date, which is a Ka-band system on MRO, delivered 6 megabits per second when Mars was at its closest. At opposition, it would take 9 years to bring back a Google map of Mars. Next slide. But if we were to develop laser communication systems, we could do it in 9 weeks. Those systems would be spec'd to deliver about 250 megabits per second, and I'll talk about that coming up. Next slide. So back in 2013, NASA did its first laser communications demonstration. I talked about this last year, so I'm not going to stay here long, except that it was very successful. We flew on the LADEE mission. We had a very small terminal, a 4-inch telescope that was able to send 600 megabits per second of data back from the moon, the distance of the moon, 400,000 kilometers back to the Earth. And just to give you a point of reference, at MPEG-4 compressed, 20 megabits per second, that's about the equivalent of 30 HD TV channels coming back from the moon. This was an effort that we did with MIT Lincoln Laboratory, NASA Goddard, NASA Ames built the spacecraft, and then we had 2 ground stations that collaborated with us at NASA JPL and ESA. And it's important that we had multiple ground stations because one of the things that affects optical communications is clouds. And clouds in turn cause dropouts in the data, which is, by the way, an excellent place for DTN to come in and help us out. So these are some of the awards that we've won with this mission here. Next slide, so I'll talk a little bit more about that. So next for the animation. So LSCD, as I said before, it flew to the moon. Actually, it launched in September 2013. We did the experiments in late 13 and early 14 last year. Next. So we made immediate contact in October of 2013, and when I say immediate contact was when we did this, it was completely successful and successful in every pass, and I'll have a little more about that. So we didn't have to spend a long time having the laser beams hunt around looking for each other, so to speak. It was a well-designed system. Next. We set records both not only in download speeds from the moon at 600 megabits per second, but also 20 megabits per second to the moon, which is 5,000 times faster than anything that had been demonstrated. We actually were able to send HD video to the moon because of that. And we ended operations in November and then started them again in April. And then in April of last year, the spacecraft itself was smashed into the moon and our payload went with it. So we don't have this anymore to do but experiments on. But again, this is what I'd emphasized before. Next slide. So there's something else about optical communications that's very, very compelling. In addition to getting a lot of bandwidth, because the wavelength of the light is so much shorter, it's about 100,000 times shorter in wavelength optically than for RF, it allows you to make smaller apertures as well in smaller systems. And so you can see on this chart that I have, the data rate is basically the height of the column here, so to speak, and we like to say that we had an S-band system to LADEE, which was a dial-up at 28 kilobits per second to the moon. LRO, which is the Lunar Reconnaissance Orbiter, that flew in 2009. And that demonstrated 100 megabits per second back from the moon, and of course we demonstrated 600 megabits per second. But you can see in the image here that the 2 spacecraft, LADEE is down in the bottom corner, up the top is LRO. These are actually to scale, and I don't have a pointer, but you can see that this here is actually our terminal, and up top you can see the RF system on the big boom. And so we were half the mass, and we used 25% less power than the comparable RF system while sending 6 times more data. Next, please. So I just said that, basically. This was our beautiful launch from Wallops Island in September. Next. And so these are some, this is a quick summary of the mission and actually how well it worked. So next in the animation. First, as I had alluded to before, we had instantaneous acquisition on every single pass. We had 54 passes during the demonstration, and every time we turned it on and aimed it, the system completely locked up, and it was not, again, even seconds of hunting around. It was perfectly every time. Next. Once we had acquired the system, next, then we narrow the beams up and we start doing the heavy transmission. Again, 20 megabits per second to the moon, 66 megabits or 622 megabits per second from the moon. We use invisible lasers, by the way, which are eye-safe wavelengths. This is important if you want to use these laser systems from the surface of the Earth up. Next. We operated through thin clouds. So this is important, and we'll have some data that'll show a little bit about this. The data rate was reduced. We had attenuation. When the clouds got heavy, of course, we completely lost the signal. That's where DTN would come in. Next. We were the first demonstration over a lunar link with DTN. Again, Dave Israel took the lead in that, and that's really his baby. Next. We also could do ranging with this system, too, less than a centimeter, and that's great for navigation as well. Next. Next. So we also operated in broad daylight close to the sun, which is what the Deep Space Network does right now. You have to be able to show you can do the same thing. Next, please. And also when the moon was low on the horizon, we operated through a very long path length of atmosphere. And this is actually important as well when the moon was low on the horizon, because when you go through that much atmosphere, you get a lot of fading. And the fades are on the order of milliseconds. And so this is another place where we would say, okay, how can the LTP help us out if we wanted to overcome losing data in a few milliseconds and then reacquiring in a few milliseconds. So these are all some of the challenges to think about. In our case, we did it in hardware using error-correcting codes and deep channel interleavers, which is basically a way to spread the code word errors out over several seconds. But DTN would be another way to consider that. This is kind of fun, by the way, the next one here. So not only did we help the Laddie Science mission by bringing back some of their data from the moon. Next, I actually have a video here that was sent.
Hello.
I don't have my sound on.
This is NASA Administrator Charlie Bolden.
This is our Administrator Charlie Bolden.
A post-laser beam transmitting
image
data
was
at
this is an HD video that was uplinked to the moon,
from our Laddie spacecraft,
looped back and sent back down
the
over the laser beam. So both directions on the uplink were uplink laser beam and downlink laser beam. Next. This is the DTN experiment. This is Dave Israel's chart, actually. Hopefully I'm not stealing too much of his thunder, but I think he's going to tell you more about what we've got planned versus what we did last year. So you can see off to the left here, the animation, please. You can see this is when the link was good. The green line up top is the received signal. So you can see we're getting a lot of power. And, of course, down below, the red dots and the blue dots are the bundles that go out and the bundles that come back. Next on the animation, then you can see, of course, some clouds came by, and we lost the link. You can see the red dots have gone away. We're not getting any bundles. They're being transmitted, but they're not being received. Next again, and then the link resumes when the signal comes back. The cloud is passed over. The lost bundles are starting to build back up. Next. And finally, the DTN protocol has caught up, and the bundles sent and bundles received are back at one again, so to speak. Next. So now I want to talk a little bit about what we have in the future, because these are future opportunities and where we're going to need DTN. Next. So deep space is really the place where optical communications to first order really seems like it's very advantageous over radio. And again, we all understand how lasers are. So RF systems, because they have much longer wavelengths, that means that their beams spread out over distance. And if you're trying to concentrate your signal power at a great distance, then a laser beam allows you to concentrate that by a factor of 100,000 times more, so you can deliver more signal power at a greater distance. So when you're trying to talk to Mars, then you can deliver more photons per bit and thus be able to deliver more bits in general. And so this is something that NASA JPL is working on right now. This is actually a funded effort called DSOC, Deep Space Optical Communications. This effort actually, the goal is to build a space-qualified laser communications deep space terminal by the end of FY17, which is only a couple of years from now. And it is to be GFE'd, provided basically by the DSOC project to the upcoming Discovery 2020 mission, which is going to be going somewhere in the solar system. All the proposals were received recently, and it hasn't been decided where it's going, but Mars is one of the prime candidates. And so this system here from Mars, you can see a link budget on the left. You can see that when Mars is at its closest, this system can deliver up to 250 megabits per second from Mars back to the Earth. Remember that the highest we've ever done with radio is 6 megabits per second. So it's quite a bit of an advance. And it's actually, again, in keeping with the small SWAP, or small size, weight, and power. It's a 28 kilogram payload that uses about 76 watts of power. So that's actually pretty small again. I want to point out as well that NASA now has very serious plans for building a Mars relay orbiter in the 2024 timeframe. At last, yeah, that's right. They canceled the other one. That's right. So it's coming back. The science teams, the Mars Science Program understands the need for this relay orbiter. We're working, SCAN, my organization, is working closely with the Science Mission Directorate at NASA headquarters to work that. And again, we're hoping to get this optical payload on that as well. So in addition to flying on Discovery 2020, to flying on that relay orbiter. Again, these are all opportunities for DTN. We've got deep space coming. Finally, it's interplanetary, and we've got a channel that is bursty and thus could take great advantage of DTN. Next slide. This is another fun study that we just completed. Very, very possible here. This is the Mars 2020 rover. We're a little bit late in the cycle of getting this on, but it is still discussed as a possibility. So we'd actually have a very small optical head. This is a 5 centimeter telescope aperture. This is much larger here than it would be in real life, so to speak. You can see it actually up on the rover, up on the top, and it's pretty small. It's about 12 pounds, and it would use 50 watts. And this system here could actually deliver in a direct-to-Earth link 200 kilobits per second when Mars is at its closest. Now that sounds pretty small, but right now we do it with X-band, and we only deliver 20 kilobits per second direct to Earth. And on this relay orbiter that we just talked about, we have plans as well to have a proximity link where we would have a terminal on the relay orbiter that would be looking down at the surface much closer. And this system could actually deliver 20 megabits per second from the surface up to the relay orbiter, and then the relay would be the big trunk line using the DSOC that I presented earlier to trunk back big data. And of course, the relay orbiter would probably use RF and optical and have RF connections. So we hope to provide some networking at Mars. Next slide. We also have a near-Earth program. Dave Israel is going to talk about this next. I'm going to cede the floor to him in a second. Next slide. So if you'll walk me through the animation here, so to speak, the next is our laser communications relay demonstration. We're going to fly in 2018, we're going to be flying on a Space Systems Loral spacecraft as a hosted payload, and we're going to geostationary orbit on a COM-bird, but we're going to be all laser comm, basically 2 laser comm terminals talking to 2 separate stations on the Earth. We can also have it connect to the space station. I'll talk about that in a bit. So what's good about this is that the payload that we're flying is going to be heavily based on what we just flew to the moon. So this is, we're trying to leverage the technology and build off of it as we can. So the optical module and all the pointing and acquisition and tracking software and all the things that we learned during the moon mission, we're going to apply here as well. But I will say that the modem system, which is the electro-optics to send all the big bits back, is quite different in getting an upgrade because we can do up to 2.88 gigabits per second with this system instead of 600 megabits per second. And one of the reasons we can do that is because we're a lot closer from GEO versus going to the moon. So there's 100 times less link loss, and so you can make that up in bandwidth. We are going to differential phase shift keying, whereas before we used pulse position modulation. Next. We're also going to have a high-speed electrical switch on board so we can switch between the 2 terminals and perhaps even connect to an RF modem on the spacecraft as well. Next. We're going to have 2 ground stations that we'll be communicating between. One is the JPL facility that we used, and then we have another that we're going to have at White Sands, please, on the animation. Both these are going to be upgraded to have adaptive optics. And then we're going to have a mission operations center next that's going to be in operation for 2 to 5 years. So remember, the LADI mission we did was 3 months long, and then we lost the payload, crashed it into the moon. It was a short experiment. This LCRD is really going to give us an opportunity to learn how to do this over the long period. And our principal investigator is David Israel, and he's going to As a matter of fact, we have an open program where we are soliciting anyone who wants to do experiments. And so if you'd like to do some experiments on LCRD over that 2 to 5 year time frame, talk to Dave Israel. We even have a commercial guest investigator program as well, so to get the commercial guys interested in optical communications. Next. This is something about marketing, and it might be applicable to Vince's question earlier today as well. So there's a classic book from Silicon Valley called Crossing the Chasm by Jeffrey Moore. It's often taught in business schools as a marketing book. And what it basically shows the technology adoption life cycle, where this is the market that you're targeting here. And so you see a normal distribution, basically a Gaussian distribution of the customer base, so to speak. And so, of course, the largest part of the distribution are, of course, the largest body of the customers. Off to the left, you have the innovators and the early adopters. And those are the folks who are not afraid of technology. They see it as an advantage. As a matter of fact, can I get my first bullet, please? So, next. So innovators, they see a competitive advantage to a new technology. They're not afraid of it. It's a disruptive product. We can put either optical communications in this. You can put DTN in this if you like. Maybe we can use this model here to maybe discuss how we push DTN forward. But the issue here is that there's a chasm, and that is that it's very difficult to get the pragmatic, largest part of the market to accept what you're trying to do, because they are not necessarily risk takers. They are, protecting their current status quo, so to speak. Next on my bullets. So these pragmatists, the way to cross the chasm, and the book does this beautifully, is to provide a complete solution to a business problem, the whole product model. So if you go to the next slide. So this is what the whole product model is. This is straight out of the book. I did give credit to Jeffrey Moore, of course, but I've made some adaptations here. So you have the generic product that you're trying to push, but then you have to have a support ecosystem all around it to make it work. You've got to basically make it so easy for your customers to use that they don't have to invent anything on their own. That's what this book is about. And so I have this again for optical comm, but maybe we should think about this in the context of DTN as well. So can I get my first bullet? So additional software. So I put DTN at the top of the list here because I think that if we develop these high bandwidth optical comm links that sometimes fade and drop out, and we don't provide DTN, our customers are not going to have a satisfying experience. We have to have DTN for this. I also would say that things, software to allow the system to be easily provisioned and planned, that needs to be in there as well. I think support equipment is required in a hardware standpoint, specifically big buffers. And fast electronics, edge electronics, so that we can do these buffer and burst capabilities. As a matter of fact, NASA has a project we're working on right now. It's at a fairly low level to do 200 gigabit per second links. And you say, gee whiz, that sounds crazy. Who on Earth needs 200 gigabit per second links? But you can see that a lot of NASA customers, like the science data customers, the PI, if he gets his data once a day, he's ecstatic, as long as it's there in the morning by the time he gets his cup of coffee. And so if you've got all day and you've got the buffer for it, if you can find a 200 gigabit per second system and burst data down in like a 5-minute interval, then a mission like NISAR, which is a synthetic aperture radar that NASA is really interested in, generates 40 terabits of data per day. And you could dump all that data in 5 minutes with a very high bandwidth link. So you have, in other words, there are customers out there that don't care about latency. And if you have the buffering for it, and buffering is cheap now, you can get big memories, and you can use a protocol like DTN, then you can deliver a ton of data and not use a lot of resources. I mean, let me compare it a different way. If you had a much lower data rate link, like a gigabit per second data rate link, it would take 100 times longer and tie up your relays and any other assets 100 times longer. So if you want to reduce the cost of your relays, or by time sharing them with other missions, then this really fast buffer and burst architecture might allow you to do a form of TDM, so to speak, time division multiplexing, and kind of spread the cost out of a relay over many missions instead of one mission tying everything up. Of course, system integration, you have to have calibration and certification. I would say maybe for the DTN analogy, some of the testing that we're doing right now on the scan testbed platform with the French, that's great for validating CCSDS work that we're doing, as a matter of fact. Commercialization. So we're leveraging a lot of COTS work. I think I heard it mentioned as well for DTN, leveraging some of the apps that are out there and trying to make it so that we don't have to build a big app space on our own, but being able to interface with that. That helps to drive the cost down and get the user base up. Next. course, for optical comm, you need a big ground network. Maybe we can, where we have to have fiber connectivity to new telescopes and places that we don't normally have fiber connectivity to, because we want to go where it's clear, and radio systems don't necessarily need that. Next. This is actually key, at least for optical comm. Non-PhD operators, that's right. I mean, when we did LLCD, we did have PhDs out on White Sands tweaking things, and you can't have that. And we probably are, I could say the same maybe about getting DTN adopted. And finally, standards and procedures. For optical comm, we have to coordinate with the FAA and the Laser Clearinghouse to make sure we don't light up airplanes and such. And we work with other agencies, and I think that your group here has this covered from a DTN standpoint in the work that you're doing with CCSDS, and maybe some new work that I heard mentioned about the IETF. So next. This is the scan network. This is actually kind of a fun animation. You can just step through this because this is my walk-off slide. But you can see basically how Space Common Nav plans to evolve its networks to use more optical. So the blue link up there is the LADI link. You can see that's the link we demonstrated in 2013. And if you step through the animation, you'll get to see some more optical links that we plan to run. There's LaserComm relay demo, Dave Israel's mission. Next. And then finally, we see missions such as deep space to Mars, an optical comm link. Of course, the traditional RF links are around as well. So with that, I'm going to cede the floor to Dave.
Well, can we do questions?
Sure. Sure, we can do that.
Okay. For your exercise point. No, I need the microphone. You have the microphone. I need the microphone. Okay, it's been again. A couple questions. First of all, you showed results that said this thing works in sunlight, and I was kind of surprised given it's infrared, especially if you're on Mars looking towards Earth and the sun is blasting away. It still works. I just want you to nod again and
it
say
does.
yes.
It does.
That is amazing. The second question has to do with LaserComm satellites. I'm with my National Science Board hat on. We've got some very big telescopes that are under construction in Chile and in Mauna Kea, like the large synoptic telescope. These things are pulling, petabits of stuff. Is anybody planning to put a LaserComm satellite in such an orbit that we could reach, for example, Chile and Hawaii with these high-speed laser links?
Well, it's possible that LCRD, if it's placed over CONUS, which is where we're planning to place it, could actually see some of these places. So you need to talk to Dave there.
We should talk about this. That would be spectacular. They would really like that. Okay, thank you.
Sure.
Any other questions?
I have a question.
Okay.
Thanks, Vint. So this is actually from the webcast. And during solar flares, there's a lot of interference, and so we have satellites up there like Stereo, SDO, that are subject to interference. And are there plans to use DTN to improve communications with those satellites during the very activities that are an area of interest to study?
That's an excellent question. I think at this point, those systems that are out in space right now, I mean, and anyone else who's a DTN expert, I'm certainly not, can probably field this one for me, but I know that for a fact they probably do not have the hardware capabilities to support buffering and bursting right now as they were launched, but perhaps something can be placed there. I don't know. Scott, do you have any?
I think what's more likely to be an issue is two things. The operating systems and processors on existing spacecraft tend to be designed to accommodate exactly what they're supposed to do with not an awful lot of leftover margin. So uploading additional software and having them do additional things for some of the older missions, I think is not going to happen. We were able to do it, for example, with the Deep Impact spacecraft because there really was some additional margin. We had room. We had a spare processor we could load it onto. That's an unusually benign kind of environment. So I don't think there's a lot of prospect for doing for doing that sort of thing with spacecraft that are more than 5 or 10 years old now. For something like the Mars Reconnaissance Orbiter, some of the other more recent Mars spacecraft, we sort of could upload more software and try doing that sort of thing. The other, well, I think that's probably the main answer. Yeah,
I have something to add too. So I talked about for the scan testbed the software-defined radios, and I think that as those make their way into space and become more ubiquitous, then I think you're going to find a lot of flexibility as well to maybe change things on the fly. You're going to have more capable processors that can be. So going forward, software-defined radios, and by the way, I didn't say this, but software-defined radio sounds like it's RF-based, but the optical systems that we fly are also software-defined. In other words, we have FPGAs, and so you can program them just as well, reprogram them. Thanks, Scott.
I'm thinking about longevity, and although the ability to update the software is very attractive, we have some spacecraft, as you know, that have been around for over 30 years, like the ones that are on their way out of the solar system. Are you thinking about capturing copies of instances of software that are on board the spacecraft, the operating system and the applications code and everything else, and hanging on to that in some kind of an archive that we could reliably expect would be around for decades, in case we have to figure out what went wrong, or we have to try to analyze a problem and so on? Is there some regular practice like that? I don't know whether I got to go again.
I don't know, because I don't work on a lot of flight missions, and I think it would, at least from what I know about operations at JPL, it would be on a mission-by-mission basis. There's not an institutional capability to do that kind of thing. Not necessarily a bad idea, but it would be an increment of a budget increment that would have to be built into the mission planning, and I think in most cases hasn't been. And that actually raises a good point. That's another consideration for uploading DTN software to existing missions, which is, in addition to the physical constraints, the system constraints, there's also sort of mission and operational and organizational constraints. The mission operators are not necessarily eager to add to the risk of the mission by letting new software be loaded to it. So until spacecraft is really an extended mission and is all done doing everything that everybody who paid for it expected it to do, there's not really a prospect for uploading more software.
It's exactly that view that might motivate keeping copies of the software around, so that you at least can understand what happened, because you have an instance of the software to look at or test in the laboratory. Okay, are there any other questions? Sounds like, David, you're up.